of an related stuff.
Yes.
Beyond that, can you just quickly help me recall what all has been covered? One is logistic and another is gradient descent.
Logistic, gradient descent, the optimization for it. I have a literally, okay, let me send you this actually. Hold on. Can you give me one
Okay.
second?
Yeah.
I've been writing down, here, this is perfect. Yeah, these are let me send you this. This will be helpful.
Okay.
WhatsApp. So J. Yes, we did. We ended with the support vector
Yeah.
machines. Support vector machines was on.
So the highlighted are ones that we have covered, is it?
Highlighted are the big topics. So like, and then
Okay.
everything underneath that is like the subtopics.
Okay. The subtopic.
Yeah.
Okay. We have done a lot of stuff actually.
So I think we've gotten up to like 26 maybe.
Okay.
Yeah, there's one hot encoding, which doesn't seem bad. Softmax.
Yeah, that will be.
So yes. And then he started with the support vector machine example. It made sense. It wasn't like very abstract. He showed like the margins, the margin width, how to determine that. So that's where we left off in class on Thursday.
Yeah. A quick warning about support vector machines. Uh, like it's a 80s kind of thing, and it has kind of like two levels to it. One is you understand the margin, and then we're trying to basically draw a tunnel in between the two classes, kind of thing, and have as less possible overlap or misclassification as possible, and then we give some penalty to them. At least for the classification problem I'm talking about, regression is slightly more complicated, but at least for classification, we are basically drawing a road in between the, let's say, red groups and green groups, and then we want as few points on the road or on the wrong side of the road, and everyone should be on the correct side of the road. This is the basic idea. So this is one level of understanding support vector machine.
Okay.
Now from here, yes. So from here you can, I mean, this is okay. This is good as first part of this. But there is entirely a different part of the thing that support vector machines achieves to do, which is people call the kernel trick.
Okay, I'm not sure. What is that called?
Okay.
Say
So
again.
kernel, KERNEL.
Kernel tree. Okay. Okay.
Kernel. Okay. So please pay attention to that when it is covered. Let me know if you have any doubts, and we'll discuss.
You said kernel trick. What was it called?
Yes, people call it kernel trick. I mean, it's trick because like somehow
Yeah.
magically we skip some calculations which you need to do.
Oh, okay. Got it.
Okay.
Okay.
So what it essentially does is, so suppose you are doing support vector machines. Let's say those pictures that you have seen, that drawing a road in between two classes and all, those are all two dimension, right?
Yes.
Yes. Now imagine your data, like you have some bunch of regressor kind of thing, like say five regressors. Then
Okay.
the picture will be in five dimension,
Yes.
and already the road picture will be a bit complicated. You can imagine like what is a road in a five-dimensional world?
Right.
It will
Yes.
be like a plane and some like one hyperplane and some a little bit of width around that hyperplane on either direction.
Yes.
Okay. And now you imagine like let's say I have a bunch of regressors, let's say x1, x2, x3, x4, x5, but I want to include their higher powers as well, like squares, cubes, and so on.
Okay.
Okay. So then basically what I'm saying is you can create more regressors out of some existing set of regressors.
You can create more regressors out of existing set of regressors. I don't
So
understand.
even if I start with five regressors, I can consider square of every column, which is like point wise, element wise squaring, and that gives me a new column.
Okay.
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 I can create like this.
Okay.
Okay. And people do this all the time. People do this even in linear models. So let's say I'm fitting y on x, but I'm not happy with the linear relationship. So I add x square and x cube.
What does
So
that
I add
that adds another dimension?
No, that doesn't add another dimension. That basically adds more regressors.
Oh, okay.
So in a classification imagination, you have to add more dimension, but from data perspective, there's nothing new I am doing. I'm just adding another column in my X data, X matrix, which is like the square of the third column is fifth column.
Okay. Got it.
So, and that's why, like we discussed, right, at some point that polynomials are also linear algebra.
Right.
Linear algebra covers polynomials also, like even though, like this is how you do it. Like you add a column of the squares, one column for the cubes, one column for the fourth power, up to whatever order you want. And then your linear algebra formulas, those least squares formula, ridge regression formula, all of them work equally well. Whatever you have learned, all that works.
Got it. Interesting.
Okay.
Interesting. Yeah.
So support vector machines does that, but it goes one step further. It says, what if I want infinite many of them?
Okay.
Okay. So
Can I ask
I
a
mean,
question? Can I ask a
yes,
question here?
yes,
Because I'm sitting in on the linear algebra course just to refresh also.
yes,
Does
yes.
this have to do with then the Taylor series approximation for something?
Uh, this is Taylor series is another application of linear algebra in some sense. I mean, Taylor series can be expressed as an application kind of thing, but this is not exactly Taylor series. It is kind of related to Taylor series. Yeah, you can think of in the opposite direction. So suppose there is a true like relationship between y and x,
Okay.
which is some y equals f of x, right?
Yeah.
And suppose we don't know what the f of x is, we are trying to learn it. That
Right.
is basically the learned part of machine learning.
Right.
Okay, we want to use our machine to learn what the f is.
Oh, okay.
Okay,
Yes.
now let's say we cannot learn the function f exactly. But if the f has a Taylor series and we know the Taylor series up to certain terms, like first 5 terms or 10 terms, then we know a good approximation.
Yes. Yes. Okay.
That is basically what we are doing.
Got it.
When we are truncating after 10, up to degree 10 or something, we are basically assuming that the function f has a Taylor series and we are truncating at 10 terms and we are trying to learn up to that.
Got it.
So we
Okay.
are not learning the f exactly, we are learning some close approximation to f.
That makes sense. How does support vector machines now come into this?
Okay, so support vector machines also can do all these things. So you can add regressor this way. But what it says is that what if I want to add infinite many regressors? So I don't want to truncate at 10. I want to go up to infinity.
Okay.
Okay.
Yes.
So
Yes.
now let's say if I want to do ordinary least squares formula that we have learned for infinite,
Yeah.
the matrices that you have becomes infinite dimensional.
Right. Right.
Okay. So like you cannot calculate all that in finite time.
Yes.
So what support vector tracing does is it introduces something called kernel. And that kernel allows you to basically do this infinite calculation in a single formula without doing the individual terms one by one.
Oh, super interesting.
Okay.
Okay.
Yes. And this is basically the hardest part of SVM and a lot of machine learning part. So if you understand this part carefully, then like the rest will be easier.
Okay. That's super interesting.
So I just wanted to
Kind
give
of,
you a heads up on that. This is like the
he was
part you need to pay
kind of
attention.
hinting at it, saying that like he was drawing the road and showing that,
Yes.
and then he said this can also be a hyperplane. So I think he
Yes.
was maybe indicating higher dimensions, but he
Yes.
hasn't got it yet.
Yes.
Okay, cool. These things are so hard to visualize too, right? With the many
Yes, yes. Once
dimensions.
it goes to higher dimension, it becomes very, very difficult to visualize
Yeah,
what is really happening there.
yeah.
So
Okay.
that's why those two-dimensional pictures are good to have in your brain,
Yeah.
like as a
Sorry,
sample picture of what the
classification.
underlying thing is.
But it's all still for classification though, right? Even as you're going to higher dimension, like the ultimate goal.
Yes, it is for classification, but SVM also has a counterpart in regression, and that has kind of similar intuition, but the formulas are a bit different.
Got it. Okay. 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 Sounds good. What would be a good, should we pick up where we left off last time then?
Yes. So what do you want to focus today? Totally. One topic you mentioned is the gradient descent. We can do that. Anything else you have in mind?
I think just a review of the sigmoid function and logistic would be good.
Yeah, we can do that.
But yes, I think gradient descent and optimization is a big one I want to review. That doesn't really completely make sense still. I mean, I guess like why we're doing it makes sense, but the
Yes,
actual gradient descent
mechanics of it.
isn't.
Okay, yes. Yeah, that is a little bit of like core math kind of stuff.
Yeah.
Yeah, and a lot of partial derivatives and gradient and all those things.
Yes.
Yes. Okay. Should we start with that?
Yes. Can we start with that then?
Yeah, let's start with that. Do you have any notes you want to particularly cover, or I just
Can
take
I
my
can
phone?
I send you the notes that he has? Is that okay?
Yes, yes, please. I think that would be good.
Can you give me 10 seconds? Give me 10 seconds.
Yeah, yeah, sure.
Where is this? Where is it? Announcements, assignments, discussion, grades, people, files, maybe. Lectures. Yes. Here. Perfect. Let me download this. Download. And I'll send this. Let me open it real quick just to make sure. Yeah, it's number 6 here, but maybe what would be, oh my gosh, this is so much. Oh, okay. I'm gonna send this to you, buddy. The gradient descent is at the bottom, but I'd like to maybe review I mean, convex makes sense. It makes sense. Maybe we start with
Yeah, convex we discussed a little bit last time also.
that one makes sense.
Mhm. Okay, I got something. Okay. So this the end is convergence for quadratic function.
No,
That's it, right?
section number 6. It should be gradient
Yes.
descent because I think it goes
Yes.
5.
6 and then 6.1 is convergence for quadratic function.
Yeah, exactly.
Okay, fine. Yeah. Okay. Uh, let me see if I have a good picture. Uh, let me share my screen.
Yes, perfect. So Jay, today you tell me whenever you need to leave. I can stay as long as you have time for. So you tell me
No,
whenever.
no worries. I have a lot of time now. Okay. So let's try to recall the idea of what we're trying to do. I will do a bit of step back and let's talk about optimization in 1D. So let's make sure that we understand our concept very well there. So we have y equals f of x, and we want to find x.
Can you make the font or zoom in maybe a little bit? So Jay?
I'll make the font bigger. It's too small, but this is the default. This is good enough.
Yes.
So we want to find x such that y is maximized. Yes, sir. Or actually better it's minimized. I mean, it's the same problem. It's just to take us minus f of x or f of x to convert to one to another. And then the first idea is that assume that f is smooth. Then let's say we found some f. So f prime of a is 0 and f double prime of a is say greater than 0. So this will be a local minimum.
Yes.
Okay. And for convex, every local minima is a global minima,
Yes.
roughly speaking. Okay.
Yes.
So that's basically all the concepts. And this local minima to global minima conversion, this is essentially why we are studying convex, because in convex you can say that local to global. Otherwise, you cannot say that.
Yes.
Okay. The rest of the theory is same. You can apply the same algorithm. It's not just guaranteed that this is a local minima or a global minima.
Yes.
So basically, we have reduced the problem of maximizing to reducing the problem of solving an equation, which is f of f prime of a equals 0.
Yes.
Okay. So let's say instead of f prime, we write g. So g of x equals 0. This is the equation we're trying to solve.
Okay.
So then let's say we start with some x naught. It can be arbitrary, it can be based on some prior knowledge or some information given to you already or whatever. So then we calculate the g of x naught and we calculate the g prime x naught. Okay? Let's say we know how to calculate these two things. Now, this assumes that you have a way to calculate g given any input, and this also assumes that you can calculate g prime given any input. So you kind of have a like we don't need to know how to calculate it, but we need to know that there is a way to calculate it.
Sorry, can you so g of x really quick is the derivative
G is
function?
the derivative. Yes.
Yes.
G of x prime. Then we need to solve. Okay.
Yes.
Now let's say G has a Taylor series.
Okay.
So G is a smooth function, it has a Taylor series. So we'll say that G of x equals G of x naught plus x minus x naught G prime x naught plus higher order term. Okay. Make sense? This is the Taylor series of the first order.
Hold on, hold on, hold on.
Yeah, pay attention. So we want to expand the G in terms of uh, Taylor series around the point x naught. So the first term is just evaluate at x naught. The second term is basically saying that what is the derivative and then multiply with x minus x naught.
What does the second term give? The second term just gives us the
Second
next.
term means that at x naught or around x naught, the rate of change is g prime. So if I move the x by delta x amount,
Yeah,
the y will change by delta y times the derivative. Delta x or delta y will be delta x into derivative.
makes
That's
sense.
what I mean.
Makes
Okay,
sense. Okay.
make sense?
Yes.
So we assume higher order terms are small. Okay,
Okay.
because we don't know how big they are, we assume they are small. Okay, this is again another round of approximation. Just like the first round was, we assume that the function has derivative, Taylor series, and the Taylor series is a good approximation and all that. So we also assume here that the higher order derivatives are small.
Yeah.
Then we basically can solve this equation to find x. Because we know that the LHS has to be 0. So if x is true solution, then LHS has to be 0 because g of x equals 0 is what we are solving. Okay, and this dot 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 part is we are ignoring, and g of x naught we know, and g prime x naught also we know. So we substitute everything except for the x value. So we solve for x.
Oh.
Okay, you can at least recognize that everything else we know except for the x in this equation.
Yeah.
If we assume that g of x is a truly a solution.
How do we know g of x naught and g prime of x naught? How do we?
Let's say I am given a methodology to calculate that.
Okay.
Either I have a formula or I know a guy who can tell me.
Okay.
Basically.
Okay.
Okay.
Got it.
So let's solve for x. So
0 equals.
So you'll have 0 equals this thing plus this, and then you can take the thing to the other side and simplify. I'll give you the final thing, looks like this. X equals x naught minus e of x naught over prime of x naught. Okay.
Okay.
So this is called Newton-Raphson. Okay. And this is basically a very standard method of solving equations in one dimension.
Got it.
Okay. Now, what is this basically doing? Let me give you the picture also. So now I want to draw a picture here. How do I draw pictures? So let's say this is a function. And then let's say we are this bothers me every time. How do I do all this? So let's say we are at here somewhere. So at that point, I know the value and the derivative. So I can draw a tangent at that point. Make sense?
Yes.
So the tangent might look like something like this.
Yes.
Okay. Now I haven't drawn the x and y axis. So let me draw the x axis also. So let's say this is the x axis. Okay.
Yes.
Now this x axis and the tangent will intersect somewhere.
Yes. Does that happen all the time? Yes, it'll happen all the time.
Because these are two lines. Unless the tangent is like horizontal, they will intersect somewhere.
Yes, exactly.
So that intersection point is basically my next target.
That
So we get a point.
intersection point is your next target. Oh, okay. So you're jumping pretty far then.
Yes. So we reach here and then we evaluate the function again. So basically we are at here. Okay.
Okay.
Now let's step back and let me undo a few things. So my tangent was here. Now let's say the x-axis is something slightly above. So I will rewrite.
Okay, good point. Good point.
Let's
Okay.
say it is here.
Yeah.
Okay. Now you can see that where the black curve intersects the x-axis and where the tangent intersects the x-axis, they are close.
Yes.
So this will be a good case, right?
What does good case mean?
Good like my tangent is giving me a good approximation of what the true line is doing.
Yes. Okay.
So my tangent will tell me that intersection is at this point on the right, but the true point is slightly to the left.
Yes.
Okay. Now, if I gradually move this line a little bit down, you can see that the gap increases.
Yes.
So as you go further and further, and then beyond a certain point, there is actually no intersection at all. So the
Yes.
tangent will be misleading.
Yes.
Okay. And this also depends on like how curvy the true function is.
Yes.
Make sense?
Yes.
If the true function is close to linear, then doesn't matter where you start, you will reach the correct point very quickly.
Yes.
But if the true function is like nowhere close to linear, it's very wiggly or very curvy kind of thing, then you might have to do a lot of iterations.
Yeah, that makes sense. Okay.
So this is basically what is happening with Newton-Raphson.
Yes. Okay.
Okay. So that's basically the background of like how the optimization works in one dimension.
So what is this equate this final x equals x naught minus that x is the new x of where that
Yes.
line intersects with
Intersects
the x.
the tangent intersects with the horizontal line.
Tangent intersects with
Okay.
the
So this is basically your next point of investigation. Now, if you calculate the value of f of x here, and you see it is very close to 0, then you'll be basically happy that, okay, I can stop here. If it's not close enough, then you will probably like do one more step of the Newton-Raphson, and you keep doing it until you are happy.
Okay, got it.
Okay. So basically we iterate on this, and then we need some stopping criterion.
Hold on, can I guess? The stopping criteria here, if I'm understanding correctly, is where g of x is equal to 0, right? Because that's where we're trying to find our minimum.
Yes. Yes. So now the question is g of x, any practical, like if you're computing something, it will not be exactly 0, right? So you have to put some thresholds. So like it is 0, it is close to 0 up to, say, it is matching up to 8 decimals, something like that.
Okay, okay.
So
Oh,
people
because
usually
it'll
use,
keep bouncing back and forth then, right? Yeah, okay.
yeah, not just bouncing, but your like calculations may have some inaccuracy on themselves for various reasons.
Yeah.
Like if you're calculating a square root somewhere in between, that
Yeah,
square root calculation is not exact in a computer.
yeah, that makes sense.
Because these are, you know about floating point and those things?
Yes, yes.
Yeah, so floating point calculations on any nonlinear operation, there will be, if you have to calculate sin x, it will be even more inaccurate and so on. So there will be, you have to tolerate for those. So we need some tolerance criteria. So we usually do on both directions. First is that like dy, I won't write it. So delta y, this should be less than some, maybe let's say epsilon. So the y value at that point should be less than epsilon. And sometimes the second criteria that people also put is the delta x is less than some delta. The reason for this is sometimes what might happen is you are doing a lot of iteration, the x value is not changing much. So maybe the convergence will happen somewhat like after 10 more iterations, but the x value won't change much anyway.
Got it.
So you stop it now, like there is no harm in stopping now.
Yeah, we're not optimizing anymore then.
Yes, it is not doing anything, it is not moving anywhere at all.
Yeah. Okay. Got it.
So these are the typical criteria that people use for this kind of optimization. And then you can also put number of iteration limits, just to be sure that.
I'm thinking on this method here then, Sujay, as we're on that one side of the global minima, we'll in this method, we're never going to actually reach the opposite side, right? Like it'll just keep
we may very well do that,
we
depending
can't.
on how the function is. I have given you a very nice example. That's why this is happening.
Okay.
But if the curve is very wiggly or something, then a lot of things can happen.
And the x that oh, I see where the line intersects, that new x could be on the other side then, right? Yeah. Okay.
So basically, the picture I have given you is a nice example of where Newton-Raphson actually works well. There are a lot of cases Newton-Raphson doesn't work well.
Got it. Okay.
And there are some alternative methods and all. Okay. Anyways, so this is like the basics of what a gradient-based method tries to do. It tries to find the gradient at that point. Based on the gradient, it draws a tangent, or it does a linear approximation in another language. And that linear approximation tells you where to go next.
Yes. Got it. Yes. Can I add, maybe if we zoom out then from this, we're doing this. Why are we doing this again?
We want to maximize or minimize something.
Yes.
And maximizing or minimizing is setting derivative to 0.
Yes. Okay. Got it. Perfect. Yes.
Now let's say we want to do this in higher dimension.
Okay.
So let's say I'm minimizing, let's say n dimension. Okay. What that means is I have y equals f of x, where f is r power n to r. So basically x is n dimension and output is one dimension.
Yeah.
This is the function we are solving. And then if the function is really nice and everything, then you can again set the derivative to 0. So for smooth case, we can set, now how do I write that? So we can do this. Okay. Now this is an n dimension equation. Basically, this is n equations together. Do you agree to that? The gradient itself is an n dimension. So gradient is basically you construct a vector of all the partial derivatives. So let's say x is x1, x2, x3. Then you take partial derivatives of x1, x2, and x3 separately,
So it'll have to
and then we want all of them to be 0.
equal to 0. So you'll have 3 equations set equal to
So
0.
we have 3 equations. Now we started with one formula. We are trying to optimize, and then we end up with n equations.
Yes.
And all of them will have x1, x2, x3.
Yes.
And if let's say the original thing had a sign of x1 somewhere, now the derivative will have a cos of x1.
Yes.
Okay. So you can imagine like things will like there will be a very complicated bunch of equations which you have to solve all of them at the same time.
Right.
So this is difficult
Yes.
in general. Like most often this will be very difficult. So we try to take shortcuts.
Okay.
Directly solving this becomes difficult. We still can do this, but we'll do that later. First,
Okay.
we'll try to see if there are any shortcuts available. So the first shortcut is that in higher dimension, the value of this derivative itself, if you calculate it at a point, it tells us something. It tells us where like what the function is doing locally there.
Believe
Okay?
that.
Just like in the one dimension, if you know the value and the derivative at a point, you can draw the tangent line.
Yes.
And that tangent line tells locally how the function is going. So for example, it tells you that around this point, the function is increasing on the right and decreasing on the left.
Yes.
And if the value is positive here, then we should look on the left-hand side of that point.
Yes.
Because we are above the horizon or above the x-axis now, and we want to touch it. And if we go to the right, we will be further away. So we should rather go to the left-hand side.
Yes.
And then if you follow that straight line exactly, then it tells you that this is like the intersection of the horizontal line and the tangent is, this is like your investigation next point. But you need not like go exactly here. You can go somewhat in that direction and basically look ahead.
Okay.
Make sense?
Yes.
Let's say I don't want to go all the through here because by that time the curve and the straight line will diverge a bit.
Yeah.
So let me like we can do like think of stopping somewhere in between and then see like check what is the local scenery.
Yes. Okay.
Okay. This becomes all the more important because in higher dimension, because now your derivative is n dimension. So there is a lot of things going on. Okay. So we are even less and less confident about the tangent telling us the full picture.
Makes sense.
Okay. And also the tangent here is a line. In higher dimension, the tangent is a plane.
Yeah.
Okay. So what we do is we try to go along the tangent, but we do not go all the way through how much the tangent is telling me to go.
All the way to the axis. Okay.
Okay. So what we do is we use the tangent itself as an information. So notice that here we have to take the divide by the second derivative here and all that.
Yeah.
Okay. Now this G prime is actually F double prime. You agree to that?
Yes, I agree to that.
So let me write this in terms of F. So this will be F prime of X naught divided by F double prime of X naught. Okay.
Yes.
So, I mean, truly speaking, applying Newton Raphson involves calculating the derivative and the second derivative for optimization.
Yes.
Okay? So here, if you look at the first derivative, role is played by the gradient. The second derivative role is played by the Hessian.
Yes.
Okay. So our Newton's method of solving this is, so I'll write x n plus 1. So n, sorry, let's say m plus 1. M is the number of iterations we are doing,
Okay.
which will be xm minus, we have to do f prime over f double prime, right?
Yes, because it
So
was
f
G,
prime,
over
yes.
G.
So f prime role will be played by this gradient of f,
Yes.
and the second derivative role will be played by the Hessian. H, I'm writing this notation, okay? And then the division will be actually this, because the Hessian is a matrix. So you cannot just divide by a matrix, you have to take the inverse of the matrix.
Inverse, yes.
Okay.
Okay.
So we have this complicated formula.
Why is it a matrix? Hold on.
Okay. So let's say if x is 3 dimension, so then we have 3 partial derivatives.
Yes. Oh, yes. And then we'll
That's
have,
why the gradient is 3, and then each of them will have 3 partial derivatives.
yes, each
So
of
it's a
them.
3 cross 3 matrix.
Yes, perfect. Okay, got it.
Okay. So Hessian calculation can be expensive.
Yes, yes, especially in higher dimensions, right? Yeah.
Yes.
Because it's inverse too, right? Yeah, exactly.
Yes. And then the inverse also. So most of the linear algebra, sorry, the optimization course, effort is spent around how to take shortcuts so that we don't calculate the Hessian and its inverse exact.
Okay.
Okay. So the first shortcut is that we ignore the Hessian altogether. This whole
I wish math was that easy.
we ignored it. So this whole matrix and then inverse, all that, we replace it by some small number.
Replace it with some small number. Okay.
Yes. As long as the number is small, it is somewhat in the right direction. Okay.
Okay.
So gradient, what happened? It got small.
Oops.
Yeah, I don't know what happened. Let me like this. Gradient method ignores capital H here and says, so do xm plus 1 equals xm minus, let's say alpha times delta.
Oh, I remember this equation.
Okay.
Okay.
So typically alpha is between 0 and 1. Okay. And typically people avoid values more than half. Most people, like somehow thumb rule is keep it below half. Although there is no like real reason to that. But so now the question is, what do we achieve out of this? The gradient of f also tells us like the values in each partial derivative, meaning in each of the directions, how much the function is changing.
Yes.
So what this will achieve is in the direction it is changing more, it would accordingly go more. So this you can think in terms of little bit like a feature selection. So suppose you are doing a regression kind of thing and you have multiple features and one feature is working very well. So you put more weightage to that feature.
Right.
Whereas another feature is not working very well, like basically is uncorrelated with the my real response. So then we basically ignore that for some time.
Right.
And what the magic is that in the next iteration, we'll calculate this gradient again. So at that point, something else might be more important and something which was important now might be less important.
Oh, interesting.
So,
Okay.
so this is how basically the gradient descent method achieves like changing direction by like naturally adapting to the local behavior.
Yes.
Okay. And I want to like I just copied this picture from Wikipedia right now. I wanted to highlight what is happening. So this is X naught. And are you familiar with this kind of contour plot?
Uh, I mean, I've seen a contour plot before, but I'm not sure how it relates here. I
So
guess
this
we're just
basically
going
the
down.
blue lines basically tells you that all the values on that line on a single blue line is equal. So
Right.
think of this as a hill. So the small circle at the center is the top of the hill,
Yep.
and then you are drawing circles which are equal elevation basically.
Yeah.
Okay, and then you are starting at x naught and you want to reach to the top of the hill. Okay,
Okay. Okay.
so now what this is saying is at x naught, just look at which direction is the steepest, which direction like is going as high as possible. So which is this direction, and go along that direction a little bit. And then again from that point, check which direction is the steepest. So you're naturally adapting towards the peak. And
Yes.
then eventually, after some iterations, you will reach here.
Yes.
Okay. So this is what gradient descent achieves.
Can you scroll?
Yeah.
Yeah. Where is your alpha in the?
Alpha is in the picture is, so you see from x0 to x1, the length,
Yeah.
that length will be some multiple of the gradient at x0. And that multiple we are choosing as alpha.
Got it.
And you can see that as the iteration changes, the length of the arrows also gets smaller because the gradient is getting smaller.
Yes.
You can see it is changing direction because the gradient is changing direction. So the relative importance that I talked about, it like is naturally adapting in the direction also, and it is also naturally adapting the size also.
Got it. Okay.
So once you are near the top, you don't want to randomly like haphazardly go in one direction by too much amount. You want to like the step size gets controlled on automatically,
Okay. Got it.
which is a good thing if the like the topography is nice like this, but it can sometimes bad also, depends on the situation.
Yeah. Going in all directions.
Yes.
Okay. So this first equation then is what you'd, yeah, that's exactly this. X to the k plus 1 equals x to the k minus. Why are we? Okay. I
So
guess
I have chosen a
so.
single alpha, but you can change the alpha step by step also.
But then I'm asking about the sign though, because I guess in the hill example, you're doing gradient ascent. So that would be
Yeah.
a plus alpha, then you're adding that alpha gradient as well.
Yes, because most of the maths people write as if you're minimizing, but the hill example is up.
Yeah. Okay.
Alternately, you can think of this as like a lake and you want to reach the bottom part of the lake.
Right. Yeah, that makes sense. Yeah.
That's the same thing. Yeah.
Okay, so that means the first equation makes sense then. I get it. Okay, so under section 6, there's the x to the k. Okay, I see that. That makes sense now. Gradient descent converges to a local minimum, and provided that is convex, it converges to a global minimum. The idea
Because the local minimum is the global minimum.
the idea behind this algorithm is to make small steps in the direction that minimizes the local first order approximation of f. First order approximation now makes sense. It's wild that all of this is honestly just math, right? Just
The 6.1.
6 point. Okay, now we're on. Okay, convergence. Okay, so now I'm scrolling.
Yes.
6.1 is convergence for
Quadratic
quadratic.
function. So this is basically telling you that like in general function, it's very difficult to imagine what is happening with the gradient descent, but we can do some exact maths if we assume the function is quadratic. Because like for quadratic, we can calculate the exact answer quickly. For
Yes.
quadratic, the derivative is linear.
Yes.
So if you take gradient of f, you have the formula with you, right? So this thing, half x transpose qx minus b transpose.
That's the
If you take
gradient, and that's the.
no, that is the function. If you take derivative, it will be qx minus b.
Oh yeah.
So my final answer is x equals q inverse b.
He was saying that that half he'll explain later, but it's a convenient way to make the derivative so that when you
Yeah,
take your,
just so that the half doesn't appear, 2 doesn't appear in the derivative.
yeah,
Because like, x square derivative has 2x.
yes, yeah.
So that 2 will appear. So that's why he has taken half x square. So we know the final answer has to be this Q inverse B. And we know what the gradient descent will be doing. So we
Wait,
can calculate.
what do you mean by final answer, Sujay? What does final answer mean?
Oh, so if f of x is this, and we are trying to minimize, right?
yeah,
Which means setting the derivative to 0.
yeah,
And the derivative is derivative is qx minus b.
yes, we determined that
So
QX
if I
minus,
set that to 0, then x will be q inverse b.
oh, because yeah, QX equals B, X equals Q inverse B. Yes, okay, I'm there. Yeah.
So just like I talked about here, right? A little bit. So for smooth case, we can set the derivative 0, and this is like n equations together. So in general, we cannot solve it. Like solving it is difficult.
Yes,
But if the function is truly quadratic, then we can solve it quickly because it's just qx equals b.
simple math
Okay?
there.
So if it's qx equals b, then solution is q inverse b, and we know the true solution. And then we can check what the gradient descent is doing and whether it's doing well or not. Okay? So that is the rest of the algebra is just like evaluating its performance.
Oh, so now
How
they've
well the grade
really
is.
plugged
Because
that
we know the
in.
correct answer, we can evaluate how good the methodology is.
So we plug that into what? We plug that into XK.
So here,
What's
x
your
plus
XK?
x star. So x
Once-
star is the true answer. And this xk plus 1 minus x star, this is basically how much is the error is after k plus 1 iterations. Makes any sense? Or I can explain again.
I'm getting lost at um that where the mouse is.
Okay, let me explain again. I will use the contour picture. Okay. So let's say we know where the exact peak is in the contour.
Okay.
Okay. And I know the starting point.
Okay.
So I can measure the distance between starting point to the peak.
Okay.
And I can measure the distance after x1 also. What is the distance to the peak?
Okay.
So if you measure these things, then we can check whether the x1 is going towards or it is going in a wrong direction.
Okay. Okay.
Okay. So just doing x1, x0 minus peak versus x1 minus peak will tell me whether I am doing any improvement or I am like basically this is wasted of time. I am going in the wrong direction or not.
Okay. Okay.
Okay. So that's why we try to calculate here xk plus 1 minus x naught, x star versus xk minus x star. And after doing some algebra, they have proved that this xk plus 1 minus x star, which is the error after k plus 1, is some multiple of the xk minus x star. So what we need to do is we can need to check whether this multiple I minus alpha q or whatever, this is less than 1 or greater than 1.
Got it. Okay. Okay,
Okay.
cool. Cool.
Yeah.
If it is greater than one, then you're going further away from the peak then.
Yes.
Got
Yes.
it. Yes. Okay, that makes sense, Sujay. Okay.
Okay.
Wait, let me see the algebra here. How did this
Yeah.
algebra work?
Let's go through the algebra slowly. So we know this xk plus 1 is xk minus alpha into del, and del we have a formula qx minus b.
Oh, duh.
So
Okay. Yeah,
we'll
they
just
just
substitute the xk plus 1 is xk minus this, and
yes.
then put qxk minus b, and
Yes.
then collect terms, and then basically expand, and then basically take everything to one part. So x naught and xk, x star and xk we collect, and then get this.
Sorry, the last step, how did they get the identity matrix XK? Oh, wait, what happened here?
Oh, so you have an xk at the front, and you have x star at the end. So you
Okay.
collect those two things. So you have a xk minus x star
Okay.
that you write as I into xk minus x star.
Okay.
And from the thing in the parenthesis after alpha, you take the q out, then you get alpha q into xk minus x star.
Yep.
So again, you collect all those things, you get I minus alpha q into xk minus x star.
Yep. Makes
Okay.
sense.
And then you take norm on both sides. So then basically the length of the distance after k plus 1 is length of distance after k times this quantity. Now this quantity is a matrix,
That quantity is a
not a
matrix.
scalar.
Yes.
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 So the corresponding thing for matrix will be the eigenvalues of singular values.
Got it.
Okay. So they take the maximum eigenvalue and the minimum eigenvalue just to be on the safe side. Where so you have some expressions where capital M and small m are the largest and smallest eigenvalue. And then they do some algebra out of that.
Why did eigenvalues come in here? I'm confused.
Because we have a size thing, right? So length versus length. Now, what is with the length of a matrix? Matrix has no concept of length, right?
Right.
But we know that along the eigenvalues directions, a matrix is basically scaling by some eigenvalue vector along the eigenvector.
Oh my
So
God.
that's basically is the concept of length of a
Oh,
matrix.
okay. Okay. Gotcha.
It's a scaling factor along that direction.
Yes. Okay. That makes sense.
Okay? And that's what is happening.
And
I mean, there is some details here which I'm skipping. If you want to actually understand this sentence by sentence, we have to go through all that.
no, that's okay. I think the math actually makes sense. I
That's
just
roughly what the math is.
to the right hand side is
And
minimum.
then you end up with some formula, nice, like this. And this basically tells you how to choose the alpha if you know those eigenvalue stuff.
That's what
But
the goal is. The goal is to choose the alpha then,
goal
right?
is to choose the alpha. Now you can choose that if you know the capital Q matrix and its eigenvalues, then alpha is 2 over sum of the max and the minimum eigenvalue.
Got it. What is that final equation with the n then? We've introduced an n.
N, oh, capital N, this thing.
Yes.
So this is telling you like if I want certain level of accuracy in my solution, how many iterations I have to do.
Ah, okay.
So this
Okay.
is same as the previous equation, just take a log on both sides and do some transformation and you get that.
Okay. So that'll tell you how many iterations you'll have to do then.
So people want to take an estimate.
We have,
This exact formula is not very important. What
okay.
is important is two things. One is that this has log of something over epsilon,
Yes.
and approximately this is proportional to kappa. The kappa is the capital M over small m.
Got it.
Yeah, very approximately this is. So this capital M over small m is the condition number of the matrix. We discussed this, I think, sometime back long. So this is like one way of showing that why the condition number of the matrix is important.
This
So if the
seems
condition number is
like
very high,
this
then
seems
you
like
need more
this.
iterations.
Yeah. I didn't hear you. I'm sorry. Can you say that again?
If the condition number is very high, meaning the largest and smallest eigenvalues are like have a very high ratio, then you need more iterations.
Oh, super interesting. Okay. Yeah, that makes
So
sense
that
based on the formula.
so those matrices are called ill conditions, and we need to spend more time solving those optimizers because the matrix is ill conditioned.
Then conceptually, I don't understand the difference between kappa and the n, the capital N. Those sound like the same thing then.
Not exactly. Capital N is the number of iterations you need to do, and we have derived some formula of that in terms of kappa.
Oh,
Kappa is a condition
because
number
kappa will tell us the ratio, and then we can say something based on that ratio. Okay.
based on that ratio.
Okay. Okay. Oh my gosh. Okay, Sujay, I've recorded, hopefully I record. Yes. Okay.
Yeah, I think we're reporting. So
I'm gonna rewatch this then this evening so that I can understand this.
If you really want, you can go through all the maths that is happening here a little bit slowly, one line
Yeah.
at a time.
Yeah,
But I think you've gotten the broad ideas of how it
exactly.
works.
Yeah, exactly. Okay, cool. Can we take a couple minute break? I just need to use the restroom real quick. Can I take a couple minute break? Okay, I'm gonna start this.
I'll stop there.
Anything else on this topic to?
There are other topics on this. For example, the Newton's method that we discussed. Let me minimize this.
Yeah, the Newton.
So, this thing, right? This is the Newton's method
Yeah,
in higher dimension. Okay? And this is the gradient method. So Newton methods, like the first thing we are doing is we're totally ignoring the Hessian, right?
yeah,
So if you want gradient method, you're totally ignoring the Hessian, which may not be a good thing always.
right.
So people try to like use the Hessian, but they don't use the Hessian exactly. They use some approximation to the Hessian.
Okay.
And how do you approximate it? And you have to maintain the inverse of it. So you don't want to calculate like a Hessian every time and calculate the approximation and then take the inverse. If you can approximate the inverse directly, then you save some time. So there are a lot of maths around those things. There are algorithms which tries to achieve that in better ways and all that.
Got it.
So there is a lot of maths that like there are algorithms which tries to achieve that.
Got it. Okay. Cool. Okay. Can you give me 2 minutes?
Yeah, so I'll stop sharing for now.
Yes.
Just ping this.
I'll stop.